Hello and welcome to another video on Joe's Physics Corner. Today we're going to solve part B here, part B and C of question 2. Okay, so yesterday we looked at question 2A and the answers for that, I'm just going to write because we have to use the answers for the first part. So the answers, if you see the previous video, you'll see that my answer to the first part was that we had u, the initial velocity u. We assigned this as u. We said this big M, the mass of the equilateral triangle would be n, and the mass of this would be n, m. This would be n, and we said that, yeah, with these in mind, we represented v prime m, v prime big M, and omega prime big M as. So we said this will say as small v, this will say as y here, and this will say as just omega. And we said that v was equal to u times 5m over n plus 5m. We said that y here, v prime, the velocity after contact of the equilateral triangle would be 2mu over n plus 5m, and we said that omega here would be, omega was 8um over nl plus 5ml. Yeah, so that was our answer to the first part here. V prime m, v prime big M, and y prime big M. The velocities, the quantities after collision. So now we're going to look at B. Let's read B. Under certain conditions, a second collision will occur between the rotating triangle. Under certain conditions, a second collision will occur between the rotating triangle and the point particle. Okay, so it wants us to determine the condition for the second collision to occur. And okay, so let's draw the diagram again. So it means that the mass hits the edge here once, and then somehow they should make a second collision on a certain time. They should be able to make a second collision after the first one. Okay, so let's say this is the center of mass of the triangle. We draw a triangle like that. Sorry, my art skills aren't that good. Okay, so there's the ball here. Ignore that. Okay, so it has collided here, and then there should be one more contact. So what do we know from this diagram over here? Well, we know that, the circle created by the edges here, we know that the ball should be inside this triangle. The center of mass, any point, just a point in the ball of the ball should be inside this circle for the collision to occur, because when you imagine this rotating, these, like, the ball should be in like these areas for the ball to be able to make contact with this triangle over here. And so it means that after the ball hits like that, there is velocity. This triangle has a velocity in whatever direction, and this also has velocity. And we figure out it. We represent their velocities with v and y over here. And what do we know? Well, my intuition tells me that these it's the ball and the triangle should both be stationary, because so their velocities must both be 0, because this, when you imagine this hitting that, and then, okay, it hit that. Oh, it can't be 0. The relative velocity of the ball to the ball relative to the velocity of the ball relative to the triangle over here should be 0. The relative velocity should be 0, so that when you look at it from the third person perspective, they are just stationary, and this this edge over here will move like that and then hit the ball here once again. So you imagine them moving stationary like that, but this one, although its center of mass is stationary, the edges are rotating so that this here, after a certain time period, would hit the ball like that and make the second collision. Okay, so that means if the velocity of the ball v relative to the center of mass of the triangle, which is given by y, the velocity of the triangle is given by y, should be 0. That means that v and y should be equal, because it means that y minus v should be 0. And so we have v equals y. So that's the condition for the second collision to occur. Okay, so we have v here, u times 5m minus n over n plus 5m. We derived that from the previous video below. There'll be a link to the previous video here, like that here. And that will be equal to 2mu over n plus 5m. Well, they have the same denominator, so we can cancel them out and say 5mu minus un is equal to 2mu. So 3mu would be equal to un. So we divide both sides by u. We get 3m is equal to n. And what does the question want us to find? Well, the question wants us to find the ratio of m divided by big M. And we said that n here we represented by, n represents big M, the mass of the triangle over here. So we get 3m is equal to big M. So that, so 3m, so m divided by m would be equal to m divided by m, which is 3m. So we get 1 over 3. That's our ratio for the second collision of this ratio between the the mass of the ball here and the mass of the triangle here. That's the ratio between their masses. Okay, so that's part B done. Let's look at part C. After the collision, what is the velocity of the particle, velocity of the triangle, and angular velocity of the triangle? So after the second collision, so you imagine the ball hitting here. The ball, look at it like that. The triangle is here. The ball was moving here like that. That's the first part. And then the second part is the collision has occurred. And so you imagine this, and then the triangle is kind of turning. It's kind of turning like that. So this going here, this going here, this going here. And the ball is at the point of contact relative. They're both moving in with a velocity like that, but because they're same, the relative velocity of the ball to the triangle, or vice versa, is 0. And it moves like that, and then it makes the contact over here. And so this part, when we say this here is 1, and this part is 2, this here is 3. Now it's 1 moves up, 2, wait, no. This is 1 here still. Sorry, the video was interrupted. Sorry. So this is, when you say this is part 1 here, this is edge, what do you call it? Vertex 1 here, vertex 2 here, vertex 3 here. Vertex 1 will not be here. Vertex 2 will not be here. Vertex 3 will not be here. And when you look at the third part, now vertex 2 will make contact. Will make this second collision with the ball here. So it would be number 2 here, number 1 has moved up here, and number 3 has moved from here to here. Number 2 here, like that, number 3 there. Number 2 has now moved here to the ball, and so it makes contact with this ball, and after that it will carry on delivering this velocity back to the ball. And if you imagine, because we know from the first part, we figured out that, well, no. We know that we have 3 equations that we used, 3 principles that we used to derive our equations to figure out these quantities. And that is number 1, conservation of linear momentum. Number 2, conservation of angular momentum. Number 3, conservation of energy, mechanical energy. And so, by intuition, we know that because when this momentum of this ball and its energy causes now at number 2 the triangle to rotate, and they also have some velocity at whatever direction, but same in the magnitude and direction, because their relative velocities here should be equal. The relative velocity of the ball relative to the triangle should be 0, and vice versa. We know that although there is velocity in some direction, it has caused, what's important is that it caused this triangle to rotate like this with here angular velocity of omega. And then when it comes back here, then we know that because due to the same principle that momentum and energy has caused this to rotate, now by the same principle, we know that if there is motion that has been induced by this motion, if it comes back here, that rotation now will do the same thing. Now that rotational momentum that moves like that will now do the same thing. And so at the first place, we know that here omega was 0, and y was also 0, and v was u was something. U was a value. There was initial velocity. And then now here u is something else. We don't know. Let's say u is x, and then y is also x, the same value, and then omega is here, a certain value that here, let's say that's c, and then we have omega equals c. And now that c, that angular momentum c is transferring its momentum and energy back to this ball over here. And so now we know that it should return to this condition over here. Anything that has been given, when it comes back, it's just by intuition we can say that the condition here will return after contact to this condition over here. So it moves like that and then back to this again. And this here is basically the same thing. This here and this here is basically the same thing, because the velocity here, the velocity vector, has the same direction and the same magnitude. And here omega is also 0. And so let's now use these values that has been given. So what would be v prime prime m, which is this v prime prime m? Well, we said that v prime prime m here would be equal to the initial velocity of the ball over here. So that would be u, which is given as the question here is as v. So v prime prime small m here would be v. What would be v prime prime big M? Well, v prime prime big M, which is the velocity of the center of mass, the linear velocity of the center of mass here, well, that, because this will, after contact, after this has delivered its angular momentum to this ball, it will now become 0. So y is 0, and we represented y as the velocity of the linear velocity of the triangle over here. And so v prime prime big M now would be here, y 0. And what would be omega prime prime big M? Well, omega prime prime big M, which is the angular velocity of the structure after the second collision, well, after rotating, it delivers its, as said before, angular momentum to this ball, so it will no longer move. And we said that it's equal to this system over here. The condition here is equal to the condition here. And so omega prime prime M would also be 0, as mentioned here. And so that's my answer to part C. So that would be answers to part B, and that would be answer to part C. Thank you, and yeah, that's my answer to question 2. You can, the first part, the part A part, which was the hardest part, the answer to that is on the previous video. And yeah, also have a look at that too. And the next video is going to be about solving here question 3. Thank you.